Sometimes I do things that remind me how much of a nerd I truly am. A couple days ago, I was getting ready to donate some clothes to the Goodwill, so I was going through all of the closets and took note of all the business shirts that I've been wearing over the years since my time in grad school and before, and current day. And I noticed some of the materials had begun to change.
Back in my day.
Early days, I noticed there was more cotton, and now I'm seeing more synthetic blends, that sort of stretchy, soft feel that more and more consumers are enjoying. And because I have a portable lab in my pocket, I decided, well, can we see those sorts of differences using a portable near-infrared spectrophotometer? So I did just that. I looked at 6 different shirts with a variety of compositions from 100% cotton to other synthetic fabrics like nylon to understand how those compositions are going to change. But I did something else. I also tracked the metadata. I took note of each of the labels. And so I will show you how I performed those experiments really quickly. And then the 2 modes by which I decided to activate the analytical data and the metadata using 2 very different approaches. Let's get started. So before I show you the data, I want to show you how easy it was to run these experiments. When I first turned this device on, all I had to do was do a quick calibration, which is to turn this on, point into the abyss, and allow it to run. Secondly, you expose this white film to the sampling surface, allow it to finish its calibration, and that's it. You're ready to go. Now you can see these are my 6 samples, but I wanted to show you how I collected the data. And it's really simple. All you have to do is just touch some point of the material, and you will see that new scan appear on the screen. Now, here is one spectrum that I just collected on this shirt. I'm not going to keep it, but I will show you what the other data look like in this context in the samples. And so now I am toggling the sample I just collected, and I will now remove that and show you what these 6 different shirts look like. Now, once the data is collected, it's immediately moved into the cloud, and so I can do more processing, or in my case, typically download this data and activate it using Python. And so these are those 6 shirts. And you can see it can be kind of difficult to interpret. This data needs some signal processing, some filtering, perhaps baseline correction, or some descattering techniques. And so it's really convenient because I can really easily download this shirt data and have it in my local directory so that I can perform my data analysis. Additionally, I was collecting the metadata on these shirts as well. So my 6 shirts, shirt 1 is 97% cotton, 3% spandex. Shirts 2 and 3 are 100% cotton, but different colors. Shirt 4 is 94% cotton with spandex. Next, we can see shirt 5 is 55% cotton, 4 spandex, and 41% polyester. And then last, we have shirt 6, which is completely synthetic, which is a nylon material. And when I was filling this shirt, it definitely felt different. And it's really cool to now see that the material was completely different compared to my other shirts. And so the first thing I want to do is actually perform agglomerative clustering, but I want to go the no-code route, but do a slight tweak. So let me just copy these results here first. And I'm going to use ChatGPT to perform my agglomerative clustering. So I'm going to ask it to activate this data by first copying this data in and then prompting it to perform agglomerative clustering on this table. And just like that, we can start to see how it processes these results. So it very quickly got the results. Here's the dendrogram from the agglomerative clustering of this shirt material. It visually represents how the shirts cluster based on their fiber composition, cotton, spandex, polyester, and nylon. You can see which shirts are more similar by how early they join in the hierarchy. And it's now prompting us to ask us to dive in further. And so let's expand this and see what we have. And based on the composition, it's saying that shirts 2 and 3 are identical. We know those are both 100% cotton, as you can see in this table here. Shirts 1 and 4 both have high 90% cotton composition with some spandex. And then shirt 5 is very different from those with half cotton, half polyester, and some spandex. And then lastly, we have shirt 6, which is very different, completely synthetic with our nylon. Now, let's see if the analytical data matches these results, where we would expect shirts 2 and 3 to be identical, considering they're both cotton, although they are different colors, and shirts 1 and 4 to be similar in those 4 shirts to be different from 5 and 6. So let's begin our analysis. I'm going to start off by just importing the libraries I commonly use in this processing. I have my own modules that I'm calling signal processing, where I will use the apply standard normal variate. This is a common transformation used for spectroscopy data to help remove some of the scattering that occurs from the optics of the device and their interaction with the various materials. So to begin, we're going to start off by reading in the data. And I've also provided a view of the metadata that I used in the ChatGPT prompt. So let me show you what this file looks like now. The file has 2 different tabs. So we have spectrum metadata, which tells us about the sample. So we have this spectrum ID key with some of the information around when these samples were collected, where they were collected, the sample ID. And then in the second tab, we have our actual analytical data. I love the fact that this data is now split apart. It's way easier to analyze, considering I oftentimes don't want to have to go and constantly clean up the metadata just to access the analytical data. And so when I read that data in, if I don't select a sheet name, here I'm just saying sheet name equals none, I will get this dictionary here where I have the spectrum metadata, which is the first tab, and I have this spectrum data here. You may not have realized that, but if you use type and pass in the data, you can see that this is a dictionary. Because this is a dictionary, we can use the keys method to get my keys. And so I have my 2 sheet names here. So we could just call this sheet names, just so you remember what that is. And let's actually convert this into a list and render sheet name. So we can see we have these 2 sheet names here. You may not see this often, but it's very helpful when you're navigating Excel files with multiple sheets in them to be able to understand these sheet IDs and then use that for further processing. Now, when you do have a dictionary and you select the key, that becomes a data frame. So let me show you really quickly. So I have DFs, and let me select this key here. And let me just use a common data frame method head. You see now we have a data frame, whereas DFs is a dictionary. So we really have a dictionary that contain data frames as values. So let's do some processing further. So to begin, I'm going to set the dictionary to wavelength nanometers and then just rename that axis to wavelength. And then I'm going to change the column names to match the column names in my metadata. So let me just show you what that data table looks like now. We have wavelength, and then we have our shirt 6, 5, 4, 3, 2, 1. The reason I'm starting with shirt 6 here is because of the chronological order in which the data is stored, but we can obviously revert this, and when we merge with the metadata, this will be corrected. So let's merge right now. I'm going to read in my metadata, which is simply this table here where I have shirt ID, and then the composition of each of those shirts, and I will save that as metadata, set the index value to 0, and you see that we have that exact output there. Next, I want to correct for the scatter of this data. So let me show you what it looks like before and after we apply SNV. So if I look at data and I plot the data, you see that the data has a lot of scatter in it. And first, let me change the resolution. So if you use this magic command here, it will automatically render each of these as a high-res figure. So let me run this again. There we go, much better. And now let's address the scattering in this data. So we know that some of these peaks should overlap more. For instance, shirts 2 and 3 are both 100% cotton, despite the difference in color. And so I expect these to be even closer. This is likely due to the difference in light scattering, different fiber thicknesses, things like that. And so let's process this data, and let me show you what that looks like again. So I'm going to take just this line here and modify it. And let's transpose this one more time. And we can see how by adjusting for the scatter, our data is now much cleaner. It looks significantly better. And this will help the clustering that we will perform later. And so what I'm doing next is first scaling the data and then merging that scaled data with my metadata. And I'm going to call that all data. And here we have that metadata table on the left, our analytical data on the right. Lastly, I'm going to use the SciPy.cluster.hierarchy library for performing my hierarchical clustering or agglomerative clustering. Then I'm going to use this dendrogram method for actually plotting the data and rendering it as a dendrogram. And so first you create your linkage. I'm going to use the word method, and then I want to plot it. This is basically a add-on to a Matplotlib figure. So we can use the plot.figure fig size to establish the size of the data. And then we will pass in our linkages, the labels, which would be the index value, where we want the actual dendrogram to render, and then how do we sort those distances. And then I'm asking to show the leaf counts. And of course, add a title, add X and Y labels, and then render that figure. When we render this, we can see that the algorithm is suggesting that shirts 1 and 3 are very similar, followed by 2 and 4. And really, these 4 shirts together would be perhaps one real cluster, because we can see that even at the next level up, it is still a really small distance based on what we see on our y-axis. So we might say that 1 through 4 are all similar, which makes a lot of sense considering that they're all very high in their cotton content, where the percent cotton is greater than 90%, although they have different amounts of synthetic fibers as well. Next, we have shirt 5, which is showing that it is different from this cluster here with a distance of 0.3. However, it's still way more similar than shirt 6, which is that nylon shirt. And these results are very similar to what ChatGPT produced just by looking at the composition from the tags on the shirt. And so now we can see how this relationship really matters, where we can now confirm the composition using analytical tools. But when we have access to that metadata, the data on the tag, it can still tell us how these shirts might feel. So next time you're in your closet and you're looking at your shirts, consider the fact that you can just use the tag to perform some data analysis. And if you have access to different types of analytical tools, you can do that as well and just see if it's confirmed. If there's anything else you'd like me to look at, let me know, like, comment, subscribe, and I'll see you in the next one. Peace.